Hello everyone. In this video, I am going to explain threaded binary tree. First of all, we have to learn what exactly the use of threaded binary tree, why we are going to learn threaded binary tree. For that thing here, as an example, I have created a binary tree of 6 nodes. In this 6 nodes, you will see that A is the root node. This entire part, that is the left subtree, and this part is the right subtree. If I am going to represent this tree as a linked list, so in that case, there is the requirement of 3 fields for each and every node. Here you can see the pictorial representation of the tree in the form of linked list. Here A is the root node, B is working as a left child, and C is here for the right hand child. In the similar way for the B, D and E is the left and right child respectively. And in case of C, F is the right child, but there is no left child in C. So what exactly the things are here? If we will see the overall structure or the configuration of this root node or any one of the specific nodes, there are 3 fields. This field is called data field. So this is data. This field is called right pointer, and this one is called left pointer. So right pointer will keep the address of right child and left pointer will keep the address of left child. And in the similar manner for each and every node it is there. Now we will see the overall node of C, D, E and F. So in that case, here there is no left child. So this left pointer is going to point to null. And the similar way, D for the D left and right child, left and right pointers both are pointing to the null. And similarly for the E and F as well. If we will count the total number of null pointer, so in that case null pointers are 1, 2, 3, 4, 5, 6, 7 null pointers, and the used pointer which is going to point any child, that is 5. You can check the things. And there are the, if we will look at the total pointers, so there are the if it is a 6 node, there are a total 12 pointers are over there. That is also explained in this way: total number of node 6. Child pointer, that means pointing to the child node, that is 5. Null pointers which is not going to point anything, that is 7. And the total pointers, which is for any one of the binary tree, we will take simply multiply by 2, that is the total number of pointers. So in the generalized term, if I'll take n nodes, so in that case used pointers means which is going to point any node or the children over there, that is n minus 1. Null pointers are n plus 1. So and the total pointers are 2n. So if we will see the things here, unused pointers are n plus 1 and used pointers are n minus 1. So in this case there is the wastage of memory. So if you are using the binary tree to represent in the form of linked list, the pointers, most of n plus 1 pointers are pointing to the null. So that is the wastage of memory. But as we know, data structure is used to utilize the memory in an optimum way here, but here we are wasting the memory. So because we are pointing to the null, so to use all these null pointers is two scientists, A.J. Perlis and C. Thornton, have devised a way to use these null pointers or null links to replace by a pointer that is called thread. So exactly the term for the null pointer, here used the term thread. So here I am writing here thread. So thread pointer, it is the thread pointer which is going to point some other nodes in the tree. So what exactly that other nodes are? So for that thing they have suggested in order traversal, and in order traversal it is told if your left link is null, so in that case left link will go to point in order predecessor, and if your right link is null, so in that case right link will point or point to the successor of the in order traversal. So here we want to learn what exactly the successor and predecessor and what exactly the in order sequence is there. So here I am explaining in order sequence, although it is written over there, that is the in order sequence, but I'm here a little bit trying to explain that thing in a way. If we are going to traverse the tree in a in order manner, so that is the sequence is somewhere. First we will traverse the left subtree, then root, and then right subtree, and that will be followed in a recursive manner. So if I want to traverse this thing over here, so the left subtree will be this left subtree, and this will also be recursively traversed in order manner. So that will, so I'm writing here LVR, that is pointing to the left, that is pointing to the root, and that is pointing to the right. So correspondingly, if I traverse the things, so D, B, E, D, B, E, and then A, and then once again there is nothing over there, then C and F. So C and F, that is the in order sequence of this tree. Now the things are here. Both the scientists have suggested to point in order successor or in order predecessor for the null pointers. So we check the things. If it is your left pointer null, so you have to like a left pointer. If it is null, left pointer is equal to null, so it will go to point, left pointer will go to point predecessor in order predecessor. And in a similar manner, if right pointer is null, so right pointer will go to point in order successor. So we have to learn what exactly the predecessor and successor over there. So if you will see this sequence for D, there is nothing before it, so its predecessor is not defined, but its successor is defined. B is its successor. In case of B, D is predecessor, E is successor. In case of E, B is predecessor, A is successor, and so on. And if I am reaching at the last, so for F, predecessor is C and successor is not defined. So we will do the things later on, what exactly would be the successor of F and the predecessor of D. So before that, whatever the pointers are null, we will try to point out for the threads in the manner of predecessor and successor. Let us check the things. For A, there is nothing null, so leave that thing. For V, it is also not null, so leave that thing. In case of C, this is pointing null. Here it is pointing null, so I'll try to check whether it is the left child or right child. If it is the left child, I look for the predecessor as I have told, and this is the in order. So C predecessor is A, so here it will go to point in this way, and this is called thread. That is yours, thread. Clear? Now I'm coming to the D, E and F. For the D, both pointers are null. So what exactly I'll do for D, I look for the predecessor. Here there is nothing for the D, so I simply drew this line and left it dangled. We will discuss that thing what exactly I'll do, but right now this pointer is dangled, means still it is a dangling pointer. Now if I'm looking for the successor of D, so that is the successor of D is B, so I pointed in this way, that is the thread over there. And for the similar case, for the E, the B is the predecessor and A is the successor. And in case of F, if I'll see the things, predecessor is C and the successor is not defined, so once again it is dangling. So if you will see the entire picture, that is here the leftmost left pointer is still dangling, not pointing anywhere, and the rightmost right pointer is still dangling, not pointing anywhere. So the things are here. All besides all these two pointers, entire thing is completely threaded. Now we have to make the uniformity. For that thing, both scientists have suggested one extra node to assume, that is called a header node. So I have created over here a header node. Now this header node will work as a root for this entire tree. So in that case, if it will be the header, so what exactly this tree will be? this tree will either go in the left hand side and right hand side. So for that case, scientists have suggested to use this entire subtree in the left side of this header node. So now this header node is as a root, so I have written that is the root, and this will work as a child. So that will be as a child. So entire subtree, whatever the binary subtree I have taken, this will work as a this entire binary tree will work as a subtree for this threaded binary tree. Now the things are over here. So left part of the your header will point to the entire tree as a subtree. So what exactly for the right hand side? Right hand side, in the right hand side, it will go to point itself. That means in the right hand side, the right hand side will work as a child itself. Left hand side, entire tree as a subtree. Right hand side, that node will go to point itself, and both will be children. So that's why here I have given the solid lines everywhere for the, you can see in the picture, everywhere in this picture, solid lines are showing the children and the dotted lines are showing the thread. So that's why for the header node I made the solid lines to represent children. The left children is left child is the entire tree, and the right pointer is pointing itself. Clear? Now the things are over here, because in the pictorial representation it is easy to say it is the dotted line and it is the solid lines, and on the basis of that we can say if it is the dotted lines, that means it is a thread. If it is the solid lines, it is a child. But in case of memory representation, we will see the things. If I am going to represent in the memory way and I am using at the rate simply to represent address, so what exactly will happen? So here if I write address of B and address of C, in the similar manner here I'll write address of F, and this will be, if I'll go to point out over there, that will go to the address of A. So in case of C, if we will see the things, address of F and address of A. So it is very difficult to distinguish between the child and thread. So for that thing, few more thing has been suggested here. Both scientists told to increase the fields by 2. So if we will increase the fields by 2, this will be, I am adding over here 2 fields over there. So this is data field, this is your left child field, this one is the right child field. This is, now after adding 2 fields, this one will be the left child left thread, and this one will be the right thread. So now after using this thing, how can we distinguish child and thread? So for that thing, now each and every node will be represented in the uniform manner. So everyone will have the 5 fields over there. So in this way there will be the 5 fields. I am creating here 5 fields, and we will learn what exactly way to make distinguished children and threads. So this part is called left thread and this part is called right thread, and that will be in each and every node. So if you have the left child, your left thread value will be 1, and if you will have the right child, then your left thread will right thread will also be 1. So here it is 1. Clear? Because in the left child this entire tree is as a subtree, and in the right child it is pointing itself, so once again it is 1. Clear? In the similar manner, if I'll see the things for A, because it has both children, so that will be 1 and 1. In case of B, I am coming. So here once again there are 2 children over there, so that is 1 and 1. Now I'll come to the C, and if I check, so in that case this is your right child, so it is 1. But in the left child, as we know it is thread, so this will go to point as a 0, not as a 1. So wherever you will have the child link as a thread, so you will put as a, in that specific field you will put 0. Clear? So here it is 0. In the same case here it is also going to point 0 and 0. This will go to point 0 and 0, because both are as a thread. Here also once again 0, so 0, and this one pointing also 0 because they are pointing over there as a thread. Now the things are over there. What exactly I'll do for these two dangling pointers? These two dangling pointers will go to point this header. So now entire thing is clear. So this is your threaded binary tree related to this binary tree. Here you can see each and every node will have 5 fields. Your header will be the root node, and entire tree will be the left subtree over here, and all the structures will be same as you are representing in the linked list way. Besides, some two more spaces has been used just to represent whether it is the 1 or 0. If left thread is equal to 1, that means it is a child, left child, and if right thread is equal to 1, that means it is a right child. So I am here writing if L thread, so here once again I am writing this thing is over here, L thread is equal to 1, that means left child exists. If it is 0, means it is thread. Clear? So you can check the things. Similarly, if you write the things for the right R thread, so in case of R thread, if I am writing, so R thread is equal to 1, that means right child, and if R thread is equal to 0, that means it is right thread. So this is the entire representation of your binary tree in the form of threaded binary tree. Here you can see each and every field is representing some memory block, and that is used in an optimum manner to save the data of a tree. That's all for this video. Thank you for watching it. Kindly subscribe and like the channel to get latest videos and updates. Few more channels are also there in the last to get latest updates in new dimensions and domains. Kindly subscribe and like them as well.